Good evening, friends and colleagues. Let me start by thanking National University of Singapore for inviting me to speak here tonight, especially Associate Professor Chudong and Professor Kilong, also Dean of the faculty. I would also like to pay tribute to Seatrium for sponsoring this lecture series as part of its gift agreement with the College of Design and Engineering. My lecture will be in two parts. The first half will be a summary of highlights from DNV's latest Energy Transition Outlook, or the ETO, as we call it in short, which is a forecast, not a scenario, of how the energy system in 10 regions and for the world in total will change through to 2050. This is the 8th edition of our annual outlook, which is launched in different places around the world. This year we had our launch in London in October. Here I will also explore how digitalization and especially AI could accelerate the decarbonization of the energy system. The second part of my lecture will focus more specifically on the energy transition in maritime, where I will be drawing on DNV's latest maritime forecast, which we launched in Hamburg earlier this year in September. So to begin with, let's look at the latest developments. This year, finally, we celebrate a milestone for humanity. Peak emissions from the production and use of energy. Of course, we do not know the exact moment when emissions will peak, but our forecast does show that from next year and onwards, emissions are likely to start declining. Sadly, the decline, as you will see, is too slow for net zero by 2050. And our forecast is that we are heading for a 2.2 degree Celsius of global warming by the end of this century. The world has in fact already been at close to 1.6 degrees above the pre-industrial average for the past 12 months, due to also El Niño effects. Climate impacts are already visible and significant. For example, the deadly flash floods in Spain earlier this month were the results of explosive downpours of rain linked to global warming. With every fraction of a degree of warming, the atmosphere can hold more moisture, leading to heavier bursts of rainfall. So peak emissions is an important moment in humanity's relationship to energy and the planet we inhabit. But what does peak emissions mean and where does it come from? Well, peak emissions is the same thing as saying that clean energy has started to replace fossil energy in absolute terms globally. And the technologies that have done most of the heavy working is batteries and solar PV, which have been performing better in the past couple of years than most forecasters expected, including ourselves. In 2023, new solar installations globally surged by 80% to reach 400 gigawatts of capacity installed in 1 year. One of the reasons solar is gaining ground so fast is because battery prices are plunging, making 24-hour solar plus storage more accessible. Battery prices fell 14% last year, and they will keep on falling. This means EVs are poised to become cheaper too, which again means that the world is still on track towards our long-standing prediction that 50% of new passenger vehicle sales worldwide will be electric by 2031. If we look more closely at the dynamics geographically leading to emissions peaking, China is a major contributor. Record EV sales there means that petroleum demand in China is beginning to ebb away. Also, record solar installations are finally edging out coal in China's power sector. And to put it in perspective, 63% of all cars, EV cars sold in the world, were sold in China last year. 58% of all renewable capacity was installed in China. Furthermore, highly competitive clean technologies from China are advancing the transition globally, but they are facing tariff backlash in some regions now. And fully protecting all homegrown clean tech supply chains may come at a too high premium that risks slowing progress on decarbonization and tackling global climate change. So there is an exceedingly difficult balance to be found here between national security, energy security, economic goals, and the Paris Agreement commitments. Not all renewables are enjoying runaway growth. We have seen growth slow in offshore wind in the last 2 years due to a mix of reliability, supply chain, and cost of financing issues. We are starting to see green shots of recovery with governments, for example, in the UK, making auctions more attractive for bidders, and new markets are opening. However, because of the totality of challenges just mentioned, we have adjusted our 2050 forecast for offshore wind down 18% versus last year. Still a massive growth, but down compared to our view last year. However, the doldrums in offshore wind are not the main challenges. Where we see least progress is with hydrogen and CCS. These technologies are critical for the decarbonization of the hard-to-electrify sectors. Several of the first commercial hydrogen energy projects that have been trying to get off the ground have stalled due to cost overruns, and in some cases have been abandoned due to market uptake uncertainty. So we have revised our long-term forecast for hydrogen and its derivatives down by 20% from last year. This means that hydrogen's share of final energy demand in 2050 drops from 5% to 4% in 2050. At current costs, which often exceeds $5 per kilogram, green hydrogen is many times more expensive per megawatt hour than natural gas in Southeast Asia. The chicken and egg problem is that to go to the more viable $2 per kilogram level that we project for the 2040s, hydrogen needs to progress through a learning curve that can only come from mass installations. The same scaling and cost challenge applies to carbon capture and storage, where our current forecast is that the investment in carbon capture during the entire forecast period, so the investment in carbon capture for the entire forecast period will be less than the amount invested in solar and wind in 2023 alone. But still significant numbers, but it puts it in perspectives. So why are nations kicking the hard-to-electrify can down the road and not tackling it with the urgency that the Paris Agreement requires? One answer surely is the diversion of national budgets towards military spending and away from energy transition investments. Also, extreme weather events are draining budgets and yet not cementing climate action. There is also the ongoing excessive cost of borrowing, which, although is easing slightly now, continues to squeeze public budgets and prolong a cost of living crisis in many households. But it is not simply a question of funding. Governments at all levels must do a much better job of tackling NIMBYism and permitting delays, because those challenges are making renewable projects less profitable in several regions. There are also rising biodiversity concerns, challenging renewable and grid developments. Excuse me. Aligning with the global biodiversity framework is important. However, regulations do not yet reflect that climate change will surpass land use changes like deforestation as the #1 cause of biodiversity loss before 2050. One of the drivers of the transition is that energy security concerns and decarbonization mostly pull in the same direction. For example, some governments have been willing recently to look past the cost disadvantage of nuclear in the interest of energy security. So we have adjusted our forecast upwards on nuclear, reflecting a willingness to pay an additional 8 to 20% for nuclear energy over imported gas, for instance. Furthermore, we see some authorities, particularly in Europe and in China, with their dependency on fossil fuel imports, are taking the all available sources approach to energy security. This inevitably leads down the path to solar and wind, because that is by far where the main action is. So to summarize, the main changes over the past year is China is moving even faster, solar and batteries booming, hydrogen and CCS at the more expensive end of the transition are struggling. And number 4, we have more conflict-ridden world, but one where energy security concerns mainly align with decarbonization. The sum of all these changes is neutral. In other words, the pace of progress is like what we saw last year. The most likely future that we see is a 50-50 split between fossil and non-fossil in 2050, which is from 80-20 today, and as you can see, very far from net zero, and a forecast associated with, with what I said earlier, a 2.2 degree future. Some of you may have seen our previous net zero reports, where we outline how the world could close the gap between our most likely forecast of 50-50 and a future that sees the world achieve a net zero emission by 2050. We have decided not to issue a pathway to net zero report this year. We believe that achieving net zero by 2050 is for all practical purposes out of reach. However, that does not mean the target is irrelevant, because every effort must be made to keep global warming as far below 2 degrees as possible. The differences, consequences, and impact are enormous. A net zero energy system is achievable with the technology we know of today. We don't need breakthrough invention, and it would be a very different and an efficient energy system, in addition to be a clean one compared to what we have today. But we will not achieve that shift without placing a price on the externalities associated with fossil fuels. In Southeast Asia, we find 3 key trends shaping the development of the region. Number 1, fossil fuel dependency, vast yet unrealized renewable potential, and pressing concerns of climate change impacts. Fossil fuels have been crucial to Southeast Asia's economic development and energy security. The coal price surge in 2023 led to higher electricity prices and financial losses for the national utilities. Although coal prices have come down in 2024, the volatility risk for the region remains. Diversifying the energy mix can mitigate these risks, enhancing both stability and environmental sustainability. The second trend is related to the renewable potential of the region. We find that Southeast Asia holds significant potential for solar and wind power. There are signs of positive development to realize this potential, for example, through the ASEAN Plan of Action for Energy Cooperation, which aims to achieve 23% renewable energy by 2025. However, we find that the progress is slow due to issues like carbon lock-in and insufficient finance and lack of technical expertise. Renewable energy is expected to grow slowly in the 2030s, according to our forecast, after which it will accelerate, potentially reaching 80% of the electricity mix by 2050, primarily through solar and solar plus storage technologies. Despite this growth, fossil fuels remain dominant in the total energy mix. I would like to emphasize that in Southeast Asia's journey to decarbonization, major savings can be gained from the adoption of cooperation across regions. The DNV team here in Singapore recently studied the benefits and implications of a Southeast Asia cross-border interconnector system during the energy transition toward a fully decarbonized power sector in the region. In summary, the study showed that regional cooperation via cross-border electricity interconnectors offer major economic net benefits and reduces resource requirements, but requires substantial additional interconnector capacity, up to 3.5 million kilometers of cable. This suggests that further research should be conducted into how regional cooperation in Southeast Asia can ease the energy transition, but our assessment shows that we would require 20% less solar development, 13% less space footprint, and a saving of $800 billion. So there is something for every nation in creating such an interconnector network. The third trend is that climate change impact is increasingly becoming an issue in Southeast Asia. This is underlined by recent extreme weather events like tropical cyclone Yagi, record-breaking rainfall in the Philippines, and deadly heat waves. These events threaten energy systems too, with significant portions of solar, wind, and grid infrastructure located in cyclone-prone areas. The demand for cooling is rapidly increasing, projected to account for nearly 30% of total electricity demand by 2050, due to rising incomes, of course, but also due to rising temperatures. Despite contributing relatively little to global emissions, Southeast Asia disproportionately suffer from climate impacts. I've been asked several times lately whether artificial intelligence can bring the sort of acceleration we need to the energy transition. While AI alone cannot deliver the energy transition, it can certainly accelerate the journey. I see 4 ways AI can help: by improving efficiency, by navigating complexity, by accelerating innovation, and by enhancing people. Let me review each one very quickly. AI can improve efficiency by optimizing energy production, distribution, and consumption. For example, AI can forecast energy demand and supply, balance the grid, reduce losses and waste, and increase energy savings. AI can also help us monitor and maintain our energy assets, such as wind turbines, solar panels, and batteries, and detect and prevent failures. All of these reduces the cost of energy. Second, AI can navigate complexity in a fast-moving transition. For example, according to the latest edition of our ETO, as I just talked about, electricity demand is expected to more than double by 2050. The global electricity grid will also more than double in terms of circuit kilometers. And renewables will see a significant growth with a 13-fold increase in solar and 9-fold increase in wind by mid-century. So there will be a lot of complexity to manage and to deal with. Third, AI can accelerate innovation by discovering novel solutions. For example, AI can help us design and engineer new materials, components, and systems that can enhance the performance and durability of renewable energy sources. But it can also be used to improve current technologies. For example, the theoretical capacity or the capacity yield from batteries is something like 9 times the current average. So there is potential for current technologies as well. AI can enhance people by amplifying the human potential on the people side, augmenting our skills, intelligence, and creativity. However, it's not a substitute of or for human judgment, values, or ethics. And it's not a solution for all our challenges. It's a partner that we need to collaborate with, learn from, and guide with care. For all this to be possible, AI needs to be trusted, particularly for industrial applications, like for instance wind farms, power grids, oil and gas installations, and ships. AI is a fluid technology that can change during design and use in ways that are hard to anticipate, and which can have real-world effects on people, assets, and the environment. This is beyond ChatGPT applications. Setting specific guardrails in place to ensure that AI is trustworthy is an important condition for AI to be deployed and reach its potential fast. However, building trust in AI is not easy. Even the best AI legislation, the EU AI Act and also the executive order in the US on AI, does not specify how AI can show compliance to the requirements. Practical mechanisms for establishing trust are needed. And that is something we at DNV have invested extensively in over the past 3 years. In November last year, we published the world's first recommended practice on how to ensure the trustworthiness of AI-enabled systems. AI has a significant potential in accelerating the energy transition. However, the development of AI-enabled systems must happen within the guardrails of assurance tools that are as impressive as the AI itself. As you know, AI itself is a very large consumer of energy, owing to the computing power needed for machine learning, training, and for inference. In other words, the use of AI. DNV agrees with the International Energy Agency that by 2026, AI's energy demand will be 2% of global electricity demand, 2%. All the way, and we believe that this will be the percentage all the way to 2050. Important to remember that electricity production is going to more than double globally by 2050. So what we are saying in effect that AI's energy demand is likely to triple globally by 2050. But the key point is that even though AI applications are likely to grow exponentially, its relative power use will not, because of multiple expected efficiencies at software, processor, and server farm levels. So to summarize, there is no doubt that AI has the potential to speed up the transition. But the speed at which AI itself is taken up will be related to advances and investment in cybersecurity and in robust new assurance routines for AI. So I believe we have the technology needed for a smart and efficient future. What we miss is a smart and bold policy that unlocks this potential. Now let me turn to the second part of my lecture, covering expected developments in the maritime energy transition through to 2050. Let me start by saying that regulations are coming to maritime that will impose a cost on emissions, impacting the asset value of existing vessels. In the EU, 2024 is the first year where ships are subject to EU emissions trading system. And next year, Fuel EU Maritime will impose a well-to-wake requirement on energy use, effectively forcing the use of qualified low greenhouse gas fuels already from next year. For the world, not only in the EU, for the world, new IMO regulations on emissions will be adopted in 2025 to enter into force mid-2027. The ongoing negotiations at the IMO are resulting in a range of measures that falls basically within two baskets. A technical element, which will be a mandate to reduce greenhouse gas fuel intensity. And secondly, an economic element, which will be a greenhouse gas emission pricing mechanism, including flexibility and compliance pooling. We see industry increasingly responding to the decarbonization pressure. And this year, half of the ordered tonnage can use LNG, LPG, or methanol in dual fuel engines, which was the same share as we saw last year, while only 1/3 of the tonnage ordered in 2022 was with alternative fuels. So there's been a significant pickup over the past 3-4 years. We also see the first orders for ammonia-fueled vessels, despite the low maturity of ammonia energy converter technology. The IMO has an ambition to achieve a 20% reduction in maritime emissions by 2030, relative to 2008. So 20% reduction. This can be done by energy savings or through the uptake of carbon neutral fuels or a combination of the two. In a set of simulations that we performed for the IMO some time ago, we see that the uncertainty span for shipping is noticeably big. As you can see here, ranging between 10% and 100% of global natural carbon neutral fuel produced. So given that the other sectors, not least aviation, will be competing for the same carbon neutral fuel, 100% share for maritime is not possible. Even a 30 to 40% share of carbon neutral fuels is still a major stretch for maritime. So the focus must be on attacking energy losses. That is by far the easiest way to cut emissions. On a ship, typically about half the fuel energy is converted into shaft power, and only about 1/3 produces propulsion thrust to overcome the resistance of moving the hull through the water. Luckily, there is a range of technologies that can help us reduce these losses, but both for new builds and for retrofits, as seen here. According to our assessment, we can save a maximum of 16% on energy in 2030. That is equivalent of operating the 55,000 smallest ships on carbon neutral fuels, or 2,500 of the largest ships. So if we save 16% of fuel consumption across the world fleet, we will save over 40 million tons of fuel per year, or 120 million tons of CO2 emissions. In this case, we would only need 10% of the global production of carbon neutral fuels to meet the IMO 2030 goal. In other words, if we do not manage to come close to the 16% energy savings on the world fleet, it will be very hard to reach the 2030 goals. There are many ways of finding efficiency improvements, and we could be discussing those in detail over a whole semester here at the College of Design and Engineering. But one obvious way is through connectivity, meaning the linking of vessels via the intranet to onshore operation centers. Essential onboard data can be used for efficiency improvements, for example, through better weather routing or early detection of propeller and hull fouling. Gathering all such information enables ship owners and charters also to comply with the emissions reporting requirements more easily. Furthermore, having transparency of information in the value chain can lead to innovation on the contracting side as well, through, for instance, sharing the costs and the benefits on the reduction of use of energy. So what are the other important takeaways from our maritime forecast? Well, we find that as much as 7% of the fuel consumed by the world fleet is imports. 7%. So green shore power can considerably reduce emissions from shipping. And with a more efficient fleet, this percentage will most likely grow. We see delays in scaling, as I mentioned earlier, in scaling hydrogen-based alternative fuels. And in this year's maritime forecast, we present an outlook for 6 technologies that have received we would say, increased attention over the past year. We have solid oxide fuel cells, we have liquefied hydrogen, we have wind-assisted propulsion, we have air lubrication systems, onboard carbon capture, and we have also nuclear propulsion. I encourage you to read our forecast for more details on these topics, as I will just comment on two of them, namely onboard carbon capture and nuclear propulsion. In overview, onboard carbon capture has the potential to become one of the most cost-effective ways of decarbonizing shipping. One of the most cost-effective ways. But, and this is a big but, for this solution to have an impact, the CCS value chain will have to be developed. For a port to be able to receive and transmit substantial amounts of CO2, ship-specific infrastructure and CO2 storage must be built. If there is a levy on CO2, for instance, revenue from that could be used to develop CCS infrastructure for shipping, and we could see the emergence of green corridors for CCS. As far as nuclear power is concerned, there are currently 160 mostly naval vessels powered with nuclear. And we find that nuclear propulsion can be a competitive option if, and here there are two big ifs, the reactor costs are in the lower range of historical costs for land-based nuclear. And second if, there is significant innovation in international regulation and treaties, such as the Nuclear Non-Proliferation Treaty. The estimated total increase in costs of the scenarios explored in our maritime forecast is compared with a business-as-usual forecast. In a decarbonized 2050, the cost of bulk transport will increase by 70%, for tankers 80%, while the cost of transporting goods in containers will double. This increasing cost of seaborne transport will be passed through the value chain to consumers as increased prices of goods. There are already movements in the markets on this topic. Pooling strategies could also help alleviate costs for ship owners. For example, one ship could overcomply with regulations by using, for instance, ammonia or e-methanol, so a good ship. The vessel could be then pooled with a vessel running on conventional fuels. Those vessels would pay a fee to join the pool, for instance, and would thus avoid paying carbon levies, for example, those imposed by Fuel EU Maritime, for a set period of time. In simulations we performed for the IMO, assessing the impact of different regulations on the world fleet, we found that pooling can reduce the total cost of greenhouse gas emissions reduction by 6%, which is significant. So, our key findings are that shore power can reduce the emissions significantly, current at 7%. Energy efficiency measures could save 16% of emissions by 2030, which is needed to meet the IMO 2030 goals because there will be not enough greenhouse or low carbon fuels available by 2030. So a combination of the two is needed. In the decarbonized 2050, the cost of seaborne transport will increase up to a factor of 2. So, ladies and gentlemen, this concludes my brief tour of DNV's research on the energy transition. And you can see some of the work here. It's all available online, including the recommended practice for artificial intelligence for free. It has been a pleasure addressing you here tonight, and I look forward to the questions or comments that you may have. Thank you for your attention.